Now, how far away should we have this? How about we make that L over 2? And you tell me what the rotational inertia is for case D here. Okay, there's our rod. It's a length L long. Has mass M. You tell me what the rotational inertia is for that rod rotating about that axis of rotation, a distance L over 2 from its endpoint. Okay, there's our formula. I for the parallel axis, we're calling that ID, is going to be I for the center of mass axis plus the mass times the distance squared between the two axes. So what do we put in for I center of mass? What do we use for I center of mass? 1/12 ml squared, right? Same as last time. And what's D? L. There's the center of mass. So that distance is capital D. And what do we get? 1/12 plus 1 is 13/12. Do they make sense here? One of these should be much smaller than the other one, right? C better be much smaller, because you can see for case C, a lot of the mass of our stick is in close to the axis of rotation, right? If it's rotating here, a lot of the mass is in very close, not contributing very much to the rotational inertia. In the second case, it's out here. Everything is much further away, and each little part of the stick contributes mr squared, right? So we're making r much bigger. So the rotational inertia is going to be much greater in case D. So just think about things like that so that the answers make sense. So 7/48, much smaller than 13/12, right? Okay. So that's the parallel axis theorem. It's not in the textbook. So review this. And with this, it's nice because with this and the sheet in the book, you can find a lot of different scenarios. Like, for example, in the book, they give it to you in the book. Yeah, they're pretty good about some of these. But let's do this example. Let's say we wanted to find the pendulum of a grandfather clock. So what does the pendulum on a grandfather clock looks like? It looks something like this, right? There's a rod. Oops. And there's something at the end. right? And this thing swings back and forth. And we wanted to know what's the rotational inertia of this. Well, we could break this up into a rod and a disk. And so I, for this whole thing, is going to be I for the rod plus I for the disk. I for the rod, we can look up. They give you the rod rotating about an endpoint in the book. This one, we need to use parallel axis theorem. Okay? So it's powerful. This technique, parallel axis theorem, plus the table in the book, gets you a lot of different scenarios. And it just makes it, even if you know how to integrate, it makes it a lot easier. Because let me give you a quick example. This one, let's say we have a solid disk. Rotating about its center point. If you know how to integrate, that's very easy to figure this one out. Okay, very easy. Let's do this example. Solid disk rotating, not about its center point, rotating about a point on the rim there. Okay, so instead of spinning about its center point, it's rotating about a point on the rim. That is not easy. Even if you're good at integrating, that one is not easy. There's no good symmetry there for setting up an integral like that. So this becomes much more difficult. But if you know your parallel axis theorem, you can do the first case and then use your parallel axis theorem to find I for the second case, and you're all set. Okay? Very powerful technique for dealing with rotational inertias.